Hi geometry students, this is Ms. Penn. Welcome to your first video notes on partitioning a segment. So we're going to run through just one example problem today on this video. Please write down everything that I write down and I can answer any of your questions in class. And we will also be definitely practicing this in class. So we've actually done a problem similar to this one. I'm just going to kind of formalize the process for you. So we are given a situation like find the coordinates of the point P that lies along the directed line segment. We're going to come back to, this keyword directed line segment from A, the point 3, 4, to B, the point 6, 10, and partitions the segment in the ratio of 2 to 3. Okay, so to kind of get the big idea of what this is talking about, because it might not be immediately clear what this is asking you to do. So we have a point A. So I'm not even gonna think about the coordinates right away. I just kind of want to get the basic idea. And then we have some point B. I'm going to put point B up here. Okay, so the problem talks about a directed line segment, right? So the idea is that a directed line segment has a direction. And in this case, it's from A to B. So the idea is we're starting at A and we're going along this way to B. So it's similar to thinking about a vector, because a vector has a distance and a direction. So then the idea is, if we understand this idea of a directed line segment as having a starting endpoint and an ending endpoint, so in this case we're starting at A. Now let's think about what it means to partition the segment in a ratio of 3 to 2. So partition is just a big word for breaking up. So you want to break up this segment from A to B so that we have a ratio of 3 to 2. And what that means is that wherever I'm putting this new point P, and I'm not exactly sure where it should go right now, but I'm going to assume it's like just eyeballing. I'm going to say point P is about there. That looks kind of ugly. Let's try drawing P in a thinner color. Okay, so there's my point P. Then the idea would be is if I break apart this segment into equal parts, I should have 3 of those equal parts on segment from A to P. So we can kind of like imagine those are each equal parts. Let's see if I can get it a little more precise. So there's 1, 2, 3, right? And then we have 4, 5. So we have partitioned this segment into 5 total parts, but the ratio of one part to the other, so if we look at from A to P, that's a 3 units distance, and then from P to B is 2 units distance. So the ratio here as we move from point A to point B is a ratio of 3 to 2. So that's just like a general understanding visually of what this problem is asking us to do. This problem is asking us to basically break this line apart into 5 equal parts and then figure out where that point P needs to be. So now I'm going to kind of give you a strategy for actually calculating exactly where that point P needs to be. And we're going to move down to the coordinate plane below in order to do this. So let's start by first plotting points A and B on the coordinate plane. So point A should be at 3, 4. And point B is at the point 6, 10. And now I'm going to draw the line connecting those 2 points. I'm going to do the best I can to draw this line. That looks pretty good. So the idea here is the first thing we need to understand is how far along the line is point P. So like what fraction of the way along the line is point P. So if you kind of think back to our big picture, if we're starting, remember that we're starting at point A and we're moving towards point B, then we should be three kind of those little segments along the way to get to point P, right? So it's 3 units out of the total number of units, which would be, in this case, it's not the 2, that's how many you have left. It would be out of a total of the 3 plus the 2, right? Because we see we had 5 total segments above. So this gives us a fraction of 3 over 5. And we know that point P is 3/5 of the distance from A to B. So that's an important idea to understand. Point P is 3/5 of the distance from A to B. Now, we can always get 3/5 as a decimal, which if you have a calculator in front of you, you would know is 0.6. And then as a percentage, that's 60%. So it's up to you if you feel more comfortable working with the 3/5 or with the 60%. But this is going to be key to figuring out exactly where point P needs to be. So the next step in this process is going to be to think about the slope from A to B. Because we know that wherever P is, it needs to lie somewhere along that same line. So it needs to have the same slope from A to P as the slope from A to B. So if I just go ahead and find the rise and the run, I'm visual, so I like to kind of just draw it out. So it looks like if I go over 1, 2, 3 units, right? And then go up 1, 2, 3, 4, 5, 6 units. So we have a rise of 6 and a run of 3. Okay, well, instead of going over 3 and up 6, I'd like to do 60% of that, or 3/5 of that, right? So the idea is you would take the rise of 6 and you'd multiply it by 3/5. Or you could also, if you prefer, you could multiply it by 0.6, right? So you could do 0.6 times 6. And what you're going to get here would be 1.8, I believe. Oh, no, wait, that was for the other one. It's going to be 3.6, sorry. So basically, instead of rising 6, I'm now going to rise 3.6. Okay? And now I'm just going to differentiate, I'm going to kind of separate this. Because the rise, it was 6, and then we did 60% of that to get the 3.6. Okay? So similarly, what we're going to do for the run is we'll do 3/5 times 6, oh sorry, times 3. Or if you prefer, you can do 0.6 times 3. And this is where you get 1.8. So then the idea again is that if we take 3 and we only run 60% of that, that means we should only go over 1.8. Now, those are your new rises and runs, but those aren't your new coordinates, right? Because you're not starting from 0, 0, right? You're starting from point A. So if you remember, point A was the point 3, 4, right? So starting from 3, 4, I need to go over the 1.8. So maybe I'm just estimating graphically for you guys. Maybe that's like about 1.8 over. And then I need to rise 3.6. So graphically, that looks something like this, right? And I get this new point P, where I've now got my ratio of 3 to 2, or point P is 60% of the way. Now, to get those precise coordinates of point P, what I'm going to need to do is I'm going to need to add the rise and the run that I got to the x coordinates of point A. So what that's going to look like just picking a new color, will be, so we had our old point A, I'm going to do this off to the side, which was 3, 4. So to the x value, I need to add the run, because that's the x distance, that's the horizontal distance. So I'd add 3, I'm adding here 1.8. So then for point P, my new x value would be 4.8. And then for my y value, I'm adding the run, which is, I'm sorry, for the y value, I'm adding the rise because that's the vertical distance, the y distance. So that would be 3.6. And then I would get an y value of 7.6. So then we get this final answer of, this is our point P, is the point 4.8, 7.6. And if we look over here on our graph at where that point P approximately looks like just by eyeballing it, it does look to be at approximately, it's somewhere between 4 and 5, and it looks closer to an x value of 5, so that's about 4.8. And then it's hard to tell, but it looks like it could be about 7.6 up there on the y value. So again, we are going to practice this process tomorrow in class, but the basic idea is you're using the rise and the run, and you're taking a fraction of that. You're taking a fraction or a percentage of the rise and a percentage of the run to figure out where that new point should go.